Hello again everyone, welcome back to ptet.chemistry channel. So this is the last subtopic in this mole calculation and stoichiometry. It's basically all about percentage yield, okay, percentage composition by mass. Remember that's by mass, and then percentage purity, how pure is your compound given appropriate data. So without further ado, I'll just show you a couple of examples where it's a lot easier to represent or to visualize this particular formula, which probably don't mean a lot of things. It basically says that the reaction is not complete. If the reaction is 100% yield, it means you actually get out completely what you should get out based on the balance equation. In reality, most reaction never give you 100% yield because what you expect to get, which is 100% yield theoretically, is always more than what you actually get out, which is actual yield. All right, due to incomplete reactions or product loss or various other reasons. In the previous subtopic, we learned about excess and limiting reactants, so you can recap that concept by watching that particular lecture tutorial. So we have excess of zinc, which is added to this HCl aqueous, so it's a solution, so it has concentration in mole per dm cube. This is in cm cube. Do not forget that 1 dm cube equal to 1000 cm cube. Therefore, if you want to convert cm cube to dm cube, you would divide by 1000. This is kind of like the primary school conversion you would have done with kilogram and gram and various other quantity. So you have excess of zinc, so do not use zinc for mole calculations, depending on what you're trying to calculate really. So what's the maximum volume of hydrogen you can get? So remember, this was in excess, so we do not use it. So if that was in excess, the HCl is limiting. Limiting, it means completely used up, so we will use that. We're also given the information on the mole of HCl, which we can work out. So the mole of HCl is the concentration times volume, or you can do volume times concentration. They mean the exact same thing. So this is the volume in dm cube. I divided by 1000, multiply by mole per dm cube, and I label it NHCl to represent it as the mole of HCl, and do this kind of thing very, very carefully. Your calculator will not show you 5.0. I've just shown it 5.0 to be appropriate number of significant figure. I guess even one significant figure would be alright because this is technically 1 sig fig. This could be interpreted as 1 sig fig or 2 sig fig, so I wouldn't be too bothered even if you forget about that. Alright, I mean calculation is probably the more important thing at this point. So there's the mole of HCl, and we want the mole of H2, so I could set up my mole ratio now, just like what we had done in the previous lecture tutorial, well, a couple of lecture tutorial ago. From the balance equation, I label this, from the balance equation, it says 1 mole of H2 is produced from 2 mole of HCl. Because I put down H2 on top, then it's 1 on top there. It doesn't matter if you got it the other way around, then this will be 2 over 1. It's always reading from your own equation, label and reading from your own equation. Because I set up mine like this, on the other side will be the actual mole that reacted. This is not actual, this is from the balance equation, the perfect stoichiometry based on balance equation. The mole of H2 is a hydrogen gas, maximum volume of hydrogen, which means it's a gas. And therefore, I can express it as volume of H2. If I use 24, so this is in dm cube, because I use 24, which is the molar volume of gas in dm cube per mole. It's given for free in the periodic table, where 1 mole of any gas, 1 mole of any gas occupy this 24 dm cube. Since I divide by 24, that volume is in dm cube. If that volume turned out to be very small, I can convert it to cm cube at the end of the reaction, but you must be aware of your unit conversion. At the bottom is the actual mole of HCl that reacted. I could have set this up immediately from the very beginning and just put this down there. I could have done that to save myself some time and also writing a lot. But anyway, it doesn't matter at this point. So I can bring this up. So bring 5 times 10 to the minus 3 up there. So 5 times 10 to the minus 3. By right, I should have volume over 24. I'm going to move up the 24 up there because I can take shortcut at this stage because I've already done enough long cut in my previous lecture tutorials, which I suggest you to revisit. And if you still can't follow this step, feel free to just write a bit longer so that you know what to do. All right. Perhaps I can just move this down here just to be a bit neater. So that is in dm cube, and I can equal it, not approximate it. I could equal it to cm cube by multiplying by 1000, because 1 dm cube is 1000 cm cube. So that gives me 60 cm cube. Ideally speaking, actually it's not ideally speaking, it's you could leave your answer as this or this, because they never ask you in a particular unit form. So you could express this or this, because the correct conversion factor means both of these are equal and both these will be accepted as your answer. The next question, so ethanol can be manufactured from glucose. So this is a reaction called fermentation. So you will do fermentation eventually in organic chemistry. That is towards the end of your course, whether you're doing IGCSE or O-level chemistry. So now we are dealing with kilogram. So since both of these will be in kilogram, I'm talking about glucose, I'm talking about ethanol, and you want the percentage yield of ethanol. This is actual, because they say even though you started for 18 kilogram of glucose, you only make 0.92 kilogram of ethanol. So this is the actual yield. From the balance equation, we got to see 1 mole of this should give you 2 mole of these. So the mole of the ethanol over the mole of the glucose. Glucose is this one, so this is glucose. This one is carbon dioxide, which means this one is ethanol. From the balance equation, I get 2 mole of ethanol from 1 mole of glucose. So we are given masses, which means I need the MR. So the molecular mass, C6H12O6, you can calculate that. MR of C2H5OH, you can calculate that. I'm just going to calculate my calculator. For the glucose, 12 times 6 plus 12 times 1 plus 6 times 16, I get 180 there. As for the ethanol, I get 12 times 2 plus 5 times 1 plus 16 plus 1. Don't forget there is another hydrogen at the end there. So I get 46. So since I'm given masses, I can do mass over MR. But we know that N equal to mass over MR. The MR is in gram per mole, which means the mass is usually in gram. But just like what I've done in one of the previous tutorial on I think work 2 or work 3, where we work with kilogram before, because we're doing ratio, if the mass on top is in kilogram, then the mass at the bottom can be in kilogram, such that the conversion factor can cancel out. Alright, so I'm going to show you in kilogram first. I want to know from these balance equations, assuming 100% yield, what is the mass of the ethanol that I expect to get. This is the mass of ethanol, because the ethanol is everything on top, and then they divide by the molar mass, divided by 46. If this is in kilogram, then the bottom bit I can do in kilogram. I get it from 18 kilogram of glucose. So 18 kilogram of glucose divided by the molar mass of glucose, which is 180. Because of the kilogram and the kilogram, if this was in gram and gram, then they'll be alright. If this is in kilogram, this has to be in kilogram for them to be okay, because the units will cancel out eventually. Alright. So what happened then is the mass of C2H5OH will be in kilogram based on how I set up this equation. I'll move all of this up there and equal to m over 46, and then I'll move the 46 up there. But I'll do everything in one step because I can cut corner now. If you cannot do this in one step, I suggest you just write it out and do it in 2 steps. Do not cut corner until you are ready to cut corner. Be very careful. These are masses, and write down the unit. So that's your first step. And they want the percentage yield. You expect that 18 kilogram of glucose should give you 9.2 kilogram, but you only get 0.92 kilogram. So be very careful. So percentage yield means how much you actually get, which is 0.92 kilogram, how much you expect to get from the balance equation based on the stoichiometry, based on the mole ratio. You expect to get 9.2 kilogram. So the yield is not very good here. You expect 9.2 kilogram, but you only get 0.92, which means this is 10% yield. There's only 10% yield. Very, very poor reaction. If you expect 100 gram, you get 10 gram out. If you expect 9.2 kilogram, you get 1/10 of it, which is 0.92 kilogram out. Now the next question is also on percentage yield. So without further ado, let's get started. This is in tons. So we know that 1 ton is equal to 1000 kilogram and 1 kilogram equal to 1000 gram. So just like the previous question, I really don't want to be working in gram because there will be quite a big number. You can do it, of course, 10 to the 6. So 1 tons is equal to 10 to the 6 gram because of 1000 and 1000. So give you 6 zeros, so 10 to the 6. But for the sake of argument, so I hope you can see that I have ammonia, which is this. I have nitrogen monoxide, which is this. This is actual because they say they reacted 100 tons of ammonia, they get this much out. So this is the actual yield. So the mole of NO over the mole of NH3, from the balance equation, I get 4 NO comes from 4 NH3, so it's 4 over 4, which of course we can simplify into, well, 4 divided by 4 is 1, 4 divided by 4 is 1, so 1 over 1, which is a very, very simple number. Now on the other side, I'll put in the actual amount that I'm expecting. Sorry, not the actual amount, okay, it is the actual amount, but it's based on the stoichiometry, which is this equation. So I know in the previous tutorials, I keep on saying this side is for the actual amount, but in this particular case, we're going to try and work out the theoretical yield, which is what we would expect to get. In reality, we actually get lesser than that, but I'll worry about this number later on. This is actual yield, you do not put it in here, okay? So I put in 100 tons of ammonia. So I should really have my MR calculation. MR of NH3 is 14 plus 3 times 1, which is 17. MR of NO is 14 plus 16, which is 30. So I put down ammonia at the bottom. So mass in tons, 100 tons over 17. So there's my mass over MR. There's my actual mole of NH3. I expect 100% reaction, which will give me 1 mole, give me 1 mole, or 4 mole will give me 4 mole. So 1 mole will give me 1 mole. So based on that, what is my mass? What is my theoretical mass of NO in tons? Because this is in tons, just like the previous question. If this was in kilogram, this would be in kilogram because these are mole ratio. These are mole ratio. So since this was in tons, I'll leave this one in tons as well to make our life a lot easier. Mass over the MR, 30. So that will give me the mole of NO over the mole of NH3. This is a theoretical yield assuming 100% reaction from the balance equation. This is the actual yield, how much you actually get out. So the mass of NO in tons is going to be 100 over 17 is equal to this, and then move up the 30, and I'll get that, and I'm aware that my answer will be in tons. So I get 176.47 tons. Alright, so that's not my final answer because what they want is percentage yield. So percentage yield means how much I actually get. I get 160 tons. How much I expect to get. I expect to get 176.47 tons, blah, blah, blah. Altogether, my percentage yield can never be more than 100% because out of the 100% I expect to get, I will almost always get slightly lesser. Okay, so 160 divided by 176.47 times 100%, I get 90.667%. And I look at the data seems to be 3 sig fig, 3 sig fig, 3 sig fig. I mean, you could interpret this as 2 sig fig if you want to, but this is definitely 3 sig fig. You haven't really done this yet, but this is among the data given. So I would say 3 sig fig would have been alright. So 3 sig fig would be 90.7%, and I should write down that this is rounded up value to 3 significant figure. When you want to do 3 significant figure, you do first, second, and third, and then you look at the fourth one. This is greater than 5, greater than or equal to 5, and therefore you add 1 more to the number before it, so it becomes 90.7% to 3 significant figure. Let's continue to the next problem. So these are the last two questions in this lecture tutorial. So I don't want to spend too long in this lecture tutorial, otherwise it become a bit tedious. So let's do this. They want the maximum mass of hydrogen iodide that can be made from that much gram of hydrogen. So you want this one and you have this one. So we don't care about the iodine. So we have H2 and we have HI. So the mole of HI over the mole of H2 from the balance equation is 2/1 because 2HI, 1H2. Now the actual amount, I want the mass. And because I want the mass, I should really find out MR of HI. From your predict table, the iodine is 127. So 1 plus 127 is 128. So the mass of HI over 128, that's the mole of HI. And I have this much mass of H2. The MR of H2 is a molecule, so it's 2 times 1, which is just 2. So it's 45.3 divided by 2. So the mass of HI, this seems like a very straightforward question. 2/1 times that divided by 2 times 128. Press that into your calculator. So 2 times 45.3 divided by 2 times 128. You get 5798.4 gram. And the thing that is given to gram, and this was given to 3 significant figure. So I should probably round this up to 3 significant figure. So 5800 gram. So your first, your second, your third, and you look at the fourth one, greater than 5, add that in, 5800 gram, 3 significant figure. So that's just 5800. I'm just looking at it. I wonder if I press a number incorrectly because it looks like I might have pressed a number incorrectly because that thing is not very big. So I don't know why I'm getting such a big number. So 2 times 45.3 divided by 2 times 128. So yeah, I do get quite a big number. So this is the mass of the HI produced. Okay. So if you spot any mistakes, do let me know. I might have made a mistake here and there, but I'm doing it in one go. So, I don't think there's any problem with the method itself. But if you spotted any mistake with the calculations, most likely it's one of these numbers that I've used or I've done the incorrect cross multiplication and stuff, which, you should always check your work. All right. On to the next question. So we have fertilizers. This fertilizer, a bag of fertilizer contains this ammonium sulfate. Ammonium sulfate is NH4 plus and SO4 2 minus. So ammonium, it's not plus 4, it's plus 1 and minus 2. When we want to get the formula, we cross multiply the value from the charge, the value. We do never ever cross multiply the ion, never ever. 2 means you have NH4 plus and NH4 plus, you have 2 of that unit and you have 1 of this unit. So what you have is 2 NH4 plus and 1 SO4 2 minus. The net charges cancel out. That's why the compound has no overall charge. And the same thing there, K plus and NO3 minus. That is a side note, something you have been able to do from a couple of months ago when we first started on formula before we did balancing equation. I suggest you go through all your formula of ions if you are still very weak at it. This is a question and calculate percentage by mass of the nitrogen. So they want first of all for ammonium sulfate. So looking at the formula for ammonium sulfate, you need to work out the MR. So there are 2 multiple. Inside the bracket, you have 1 nitrogen, so 1 times 14 plus 4 times 1. And then you have 1 sulfur, so 32 times 1 plus 16 times 4. So the MR total up to 132. And to work out the percentage of nitrogen, you gotta work out of the 132, what is the mass composition that give you nitrogen? So there's 2 nitrogen because 1 times 2. So each nitrogen has a mass of 14. So 1 times 2, sorry, not 1 times 2, 14 times 2 out of the 132 times 100%. That is the percentage of nitrogen in that ammonium sulfate. So there's 3 significant figure. But what are we doing, by the way? So both of them have the same mass. So I guess what I should do is they want the percentage by mass of nitrogen in the bag of fertilizers. I wonder if I do need to use the 500. Well, I know that out of the 132, 14 over 2, out of the 132, so 21.2% is nitrogen. So if they want the mass of nitrogen, it would do 21 over 2 times 100%, over 100 times 500 gram. That will be the mass of nitrogen in this particular thing here. But they want the percentage by mass, so this is perfectly all right. The 500 gram is there to try and confuse you between what is percentage by mass versus what is mass of nitrogen. Percentage has a unit of percentage, mass of nitrogen will have a unit of gram or kilogram, etc., etc. The next thing was potassium nitrate. So the MR of potassium nitrate is 39 times 1 plus 14 times 1 plus 16 times 3. So what you get is 101. So out of the 101, you will have percentage of nitrogen is going to just be 1 nitrogen. So it's 14 times 1 over 101 times 100%. So I get 13.9% to 3 significant figure. Going back to the original question, they say calculate the percentage by mass of nitrogen in the bag of fertilizer. Okay, I think I get what they're trying to say now. This bag of fertilizer is 1 kilogram total. 1 kilogram total, because there are some nitrogen from this and there's some nitrogen from that. So it looks like I do need to use the 500 gram. So looks like I'm running out of space here. Anyway, so what is the mass of nitrogen? The mass of nitrogen is going to be I wonder if I should do this. Hang on. So the mass of nitrogen is that composition times 500 gram. So out of the 500 gram, how many gram is nitrogen? So 106 gram is nitrogen. And I'll do the same thing for the bottom thing because they want out of the whole 1 kilo later on. So they want the mass of nitrogen and they want it out of the 500 gram. So that will be the mass of nitrogen in the potassium nitrate. That will be times 500 gram as well. So only 69.3 gram is the nitrogen. So what happened then is in step 3, I have 500 gram and 500 grams, so total of 1000 gram. So the percentage of nitrogen in the 1000 gram is going to be this plus this, which is how much nitrogen there is, 106 plus 69.3 gram times 100%. Out of the 1000 gram, this is the mass of nitrogen from the ammonium sulfate. This is the mass of the nitrogen from the potassium nitrate out of the 1000 gram. And then I can express it in terms of percentage. So 106 plus 69.3 give me 175.3 divided by 1000 times 100, I get 17.53. Probably round it up to 17.5%, 3 significant figure. And they will tell me the percentage still, but it's in the bag of fertilizer, which contain a mixture of this ammonium sulfate and ammonium nitrate, 500 gram, which was why my strategy was to work out the mass of nitrogen in each of the respective substance first. Jumping on to the next question. So now they want us to work out which fertilizer contains the greater percentage of nitrogen by mass. This is a very popular exam questions. As you could see, for 3 marks, you got to be able to work out at least the MR. So NH4NO3 first of all. So you should be able to key in your calculator 14 times 1 plus 4 times 1 plus 14 times 1 plus 16 times 3. So they give me 80. And I should work out the percentage of nitrogen by mass. So there are 2 nitrogen. There are 2 nitrogen because 1 in the ammonium and 1 in the nitrate. So there's 2 times 14 over 80 times 100%. So they give me 35% of nitrogen, 35% by mass of nitrogen in ammonium nitrate. And I'll work out the next one. This is ammonium NH4 twice HPO4. So be very careful what they have given you. So I have 2 times 14 times 1 plus 4 times 1, that is 18. And then I have hydrogen, which is 1, plus phosphorus, which is 31, and then 16 times 4, which is 96. So I'm trying to do my calculation step by step so that I'm not making any senseless mistake, because one mistake is all it takes. And there are also 2 nitrogen, because there's 1 in the bracket, NH4, and there are 2 of them, so altogether there are 2 nitrogen in the whole compound. So 2 times 14 over 132 times 100%. I get 21.2%. So this says show by calculation which of these fertilizer. So very clearly, therefore, NH4NO3 has a greater percentage by mass of nitrogen. All right. And last but not least, what do we have here? So we have a calcium carbonate, which is, sandstone is a mixture. So it contains the silicon dioxide. Silicon dioxide was first covered as a giant covalent structure or giant molecular structure. Calcium carbonate is an organic compound. Sorry, not an organic compound, but an inorganic compound. Is a giant ionic structure. Hope you remember what is ionic and what is covalent. So what happened is you have excess sandstone reacted with dilute hydrochloric acid. Now the total mass loss. The total mass loss will be from the CO2, because this is a gas, this is liquid, and this will be in the solution. So the mass loss will be CO2. That's number one thing that you should be worried about. And out of the sandstone, which has silicon dioxide and calcium carbonate, only the calcium carbonate reacts with the HCl. So only CaCO3 reacts, not the SiO2. So what I can say is, from this equation, the mole of calcium carbonate over the mole of CO2, I want to know how much calcium carbonate is present in this 10 gram, which is why they want the percentage by mass of calcium carbonate in the sandstone. Out of the 10 gram, what is the mass of calcium carbonate present? Okay, so let the mass of calcium carbonate present be M. Let's say, let the mass of CaCO3 in the sandstone be MCaCO3, just like that. From the balance equation, so 1 mole of calcium carbonate give you 1 mole of CO2, so it's 1/1. I have the mass of calcium carbonate there because I want to do the actual mole of calcium carbonate that actually reacted. So I'll need to divide by the MR. If I do the MR of calcium carbonate on the side, so you can do 40 for calcium times 1 plus 12 times 1 plus 16 times 3, I get 100. So what I'll do is I will get the MR of CaCO3 is 100. So there is mass of MR, which is the actual mole of calcium carbonate. At the bottom, I have the mass loss. So this is mass of CO2. And because I'm given the mass of CO2, I cannot use molar volume because I'm dealing with reacting masses. So be very, very careful. So the MR of CO2 is going to be 12 plus 16 times 2. That's 44. So what you have at the bottom there is 0.88 gram of CO2 divided by 44. So our job really is find the mass of calcium carbonate that reacted. So there's 0.88 over 44 times 1/1 times 100. And that give me 2 gram. So I can say there's 2 gram. Running out of space down there, perhaps I can just write it down there, 2 gram. Alright, so out of the sandstone, there's 10 gram of it, only 2 gram of calcium carbonate that actually reacted. So only 2 gram, so percentage by mass of the calcium carbonate. Out of the 10 gram of the sandstone, only 2 gram is calcium carbonate. So put that into calculator and you will get 20% exactly. Alright, that's it for this lecture tutorials where we have covered through a couple of questions involving percentage composition by mass, involving percentage purity, such as this. So out of the sandstone, it's not 100% pure calcium carbonate, only 20% of it is calcium carbonate, etc., etc. A lot of it comes down to putting into this kind of expression, what is your unknown and what do you understand by it. Earlier in these examples, I also talked a little bit about percentage yield as well, where not everything you get is going to be 100% yield. So you got to think about how much you expect to get per the balance equation and express it how much you actually get out of what you expect to get. That will be a percentage yield of the reaction. That's it for this lecture tutorial. So do subscribe to the channel, click the button on the bottom right, as easy as that, and share the channel widely with all your friends, chat group, juniors, seniors, and various other people whomever you think this kind of tutorial videos will be helpful for. And follow me at ptet.chemistry, that is ptet.chemistry on Facebook, Instagram, and Twitter to get connected. See you in the next lecture tutorial.